to, I want this screen, into nth roots and real exponents. Okay, can everybody see the book? It's on page P14 in McGraw-Hill. If you want to follow along that way, that's fine. But I'll share the screen and bounce back and forth as we do it. Okay. So when you're considering nth roots, a key thing that we want to realize is that we're not going to be dealing with imaginary numbers. Yes, we can take the square root of a negative number, but we have to use that imaginary unit. Okay, so we don't want that. We're looking for straight real numbers in this situation. Okay, and it says the key concept, the nth root of a number. It says let A and B be real numbers and let n be any positive integer greater than 1. If A is equal to b to the n power, then b is the nth root of A. Okay, so that could be a square root as the index for n. It could be to the 4th power, it could be to the 5th power. Sometimes we'll get all the way up into the 6th power. Okay, but the key concept is the principal nth root of A is denoted by the radical expression, nth root of A, where n is the index of the radical and A is the radicand. And then you can see they give us some examples. So some examples of nth roots are listed below. So we're given the 4th root of 81 is equal to 3. Okay, so for the how would you say that? Not cube root, quartic root of 81 is equal to 3. And then if you look, you have a negative 4th root of 81 is equal to a negative 3. Another key thing is we want to pay attention to where this negative falls. Okay, if it's a negative value on the outside, we're going to have, and our index is even, meaning it's a 2, a 4, or a 6, we're going to have a negative answer here. Okay, then you have plus or minus, the 4th root of 81 is equal to plus or minus 3. Okay, and then that brings us to real nth roots of real numbers. Suppose n is an integer greater than 1 and a is a real number. In this situation, we have to realize that n is the index. Okay, that's the number that's written really small. And a is what's known as the radicand. So to understand this graph, we got to understand this basic portion right here. Let me spotlight my video. Got to make sure that's there. Okay, it's working here. This n is called the index. Okay, what's underneath is A is known as the radicand, or what is underneath the radical. So we have to understand where these two fall to make this table make sense. Okay, so going back to it. Okay, so it gives us certain situations. You can see we have an A column, an n is even column, an n is odd column. And the first one, it says if A is greater than 0, what that means is that A is positive. Okay, so when A is positive, if our index value is even, we're going to have one positive and one negative root. That's because we're taking numbers multiplied against them an even amount of times. Right, it's like taking negative 3 to the 4th power. We'd have negative 3 times negative 3, which would give you 9. And then we would take negative 3 times 9, which would give you a negative 27. But then we would take negative 27 times negative 3 again to get a positive 81. So the exponent value determines how many times we're going to multiply this against itself. So if we're multiplying a negative number against itself an even amount of times, we're going to get a positive answer. Okay, and then if we're multiplying a positive number against itself an infinite amount of times, we're going to get a positive, because a positive times a positive is always positive. A negative times a negative is always positive. And a positive times a negative is always negative. Okay, so that's it. A is positive and n is even. If A is positive and n is odd, you can see that we have 1 positive and 0 negative real roots. Okay, and what's that saying is because our radicand is positive, we cannot get that by multiplying a negative number against itself an odd amount of times. Okay, that can only be done if we multiply a negative number against itself an even amount of times. So example of that would be the cube root of 27. Okay, where n is 3, that's our index. The radicand is 27. And then we would be able to take that and we would get our answer of 3. Okay, so now let's bounce one down. When a is negative or a is less than 0, you can see if we have an even index, we have 0 real roots. Okay, that in order to take that root, we would have to use the imaginary unit of I, which isn't real. And remember, in this situation, we're only dealing with real roots. Okay, so if a is negative or less than 0, and our index is odd, we're going to have 0 positive and 1 negative real root. Okay, so that would be like the cube root of a negative 27, which would be negative 3. Cube root means we're going to multiply negative 3 against itself 3 times. Negative 3 times negative 3 is 9. Times a negative 3 again makes a negative 27. And then if a is 0, or our radicand is 0, we're always going to have 1 real root being 0. Okay, and that's because anything multiplied against itself would be 0, and since we're using exponents, 0 is the only thing that multiplied against itself where you can get 0. Okay, so that's a key step. Are there any questions about that? Key points from that is we're only dealing with real numbers. So if we're trying to take the square root of a negative number, it's not a real number, and that's all we have to put. Okay, we don't have to break it down to the odds. Alrighty, and then here we got a couple properties. Some of them are going to be new. Some of them we've covered before. Okay, and this is just understanding how it works. These properties are going to come into play. First thing is multiplication of exponents. Realize that when we multiply our exponents, so I have x squared times x to the 4th, that is equivalent to x to the 6th. A luxury is we have the substitution property of equality that we covered in Algebra 2, which states as long as they are equal, anything can be substituted in. So in this situation, knowing that x squared times x to the 4th is equivalent to x to the 6th, in an equation, if we're given x to the 6th, we would be able to plug in x squared times x to the 4th to be able to simplify. And we do that as kind of a loophole to help us simplify. We want to get it into the simplest form for us to be able to use. And you'll see it as we get through into the examples. I know it sounds a little funny, right? But we want to get it into a form that allows us to simplify it the easiest way possible. The next one is division with exponents that have, or variables with exponents that are the same variable. So I have x to the 4th divided by x squared. That is equal to x squared. Once again, because of the substitution property of x of equality, if we see x squared, we could really plug in x to the 4th over x squared. Okay, because those are two equivalent terms. They're going to equal each other. Okay, the next one is the power property of exponents. And what it states is that if we have a variable with an exponent that's raised to an exponent, so you can see I have x cubed inside of the parentheses, and that's raised to the 4th power, that's going to be equal to x to the 12th. Okay, we multiply the exponents in that situation. Once again, because the substitution property of equality, when we're given x to the 12th, we could substitute x to the third to the fourth power. And you'll see it because we're trying to get it into the simplest form and we want to make it easy on ourselves. Right? But we have to trust and know these properties to make it work. The two that are discussed in the book, and you'll see them on page P15, they're at the very top, is the product property of radicals. And what it says is that if we have the nth root of A times the nth root of B, that is equivalent to the nth root of A times B. So we would be able to multiply those two together. It allows us to expand radicals and also bring them back together. Okay, once again, the idea is to put it into its simplest form. So knowing this, same thing happens. If we have the nth root of A times B, that is equal to the nth root of A times the nth root of B. Okay, and we're going to be very strategic on how we use these. The final property that you need to know, and that's discussed in the book, is the quotient property. And what it says is that if we have the nth root of A divided by B, so A divided by B is our radicand, that is equivalent to the nth root of A divided by the nth root of B. Okay? So once again, it works both ways. We can flip that. We have the nth root of A divided by the nth root of B. That is equivalent to the nth root of A divided by B. Okay, and those are the properties that are going to come into play today. I'm going to give you a couple seconds or a couple minutes to write those down. And then we're off to working on examples. Where'd my mouse go? There it is. All right, so now let's get to the examples. Make sure I'm able to finish it before 10 o'clock. That way we can get you turned on to your homework. Okay, so the first one, example 1, on page P14, it says find nth roots. First one it gives us is A. It asks us to find the negative square root of 49. Once again, since our negative is on the outside, we can do this and we're going to get a real number. Okay, so you'd ask yourself, what's the square root of 49? Well, the square root of 49 is 7. Our negative is on the outside, so our answer would be a negative 7. Okay, because that is what it's asking us. It's asking us to evaluate that. Okay. For letter B, we're given, we want to find the cube root of 64 over 27. Okay. And this is where our quotient property of radicals is going to take into place. That these are equivalent statements. The cube root of 64 divided by 27 is equivalent to the cube root of 64 divided by the cube root of 27. The beautiful thing is these are both perfect cubes. We just have to determine them. You can use your calculator to help you with this using radical exponents. Okay, so the cube root of 64 is 4. 4 times 4 is 16. Times 4 again does give you 64. Okay, and then the cube root of 27 is also 3. 3 times 3 is 9. Times 3 again is 27. So our answer would be 4/3. Okay, once again, just taking the cube roots. Letter C. It asks us to find the fourth root of negative 21. Okay, here we want to pay attention because this falls in to that table that's at the top of page P14. We have a negative radicand with an even index. So if we look at that table, it says that when A is negative, like it is here, and our index is even, that is in here, like it is here, this corresponds to no real roots. Okay, that's because we cannot take a number multiply itself against itself an even amount of times and get a negative number. That's because a negative times a negative is a positive. Positive times a negative is negative. Okay, it would have to be an odd amount of times in order for us to be able to solve this. Another thing is 121, the square root of 121 is 11. And since 11 is prime, can't really make that work while using an even amount. So you can see some of these are going to be very easy, but they do get a little bit more complex because they do require you to use those properties. And you're going to use basically all of them. Okay, so we're off to example 2 on page P15. And you can see now it wants us to simplify. First one is the 6th root of n to the 18th. Okay, what we can do, and we can be strategic about this, is we can use the power property of exponents to get this into a simpler fashion, right? Because 6 is a factor of 18. So I'm going to think of what do I need to multiply 6 by to get it to equal 18? And the answer to that is going to be 3. So since n to the 3rd, if it's raised to the 6th power, is equivalent to n to the 18th, I'm going to substitute this in as my first step. Okay? What that allows us to do is to rewrite our equation to look like this. Okay, so now we're taking the 6th root of a radicand that's been raised to the 6th power. Okay, so it's like taking the square root of x squared. The square root of x squared is x. Okay, so since I was strategic and I used the substitution property of equality and my power of a power property, knowing that I can resubstitute back in, this turns itself into a very, very easy problem. What's the 6th root of n cubed to the 6th power? Well, that's just n to the 3rd. Okay? Since we have an odd index or an odd exponent, we would have to take the absolute value here because it is possible to get a negative number. Okay, for that. Now we're off to B. Okay, and B asks us to find the 4th root of 81 times the quantity of a plus 1 to the 12th. Okay, and once again, I want to use my power of a power property. Okay, so the 4th root of 81 is 3. 3 times 3 is 9, times 3 is 27, times 3 again is 81. So I'm going to rewrite this in a very strategic fashion. I'm going to try to get it to the best way that I can. I'm going to rewrite it as the 4th root, brackets around 3, times a plus 1 to cubed to the 4th power. And that's all in my radicand. Okay? And what we have to realize is that these two things are equivalent. Okay? All I did was rewrite it, knowing the information that I know. I knew that the 4th root of 81 is 3. Okay? So to make it easier, and to break up this 12, I use power over power, because that's a plus 1 times itself 12 times. And since I use power over power, I tried to isolate my 4. So now it comes into the same type of equation as the last one, where we're taking the 4th root of things that are raised to the 4th power. So the simplified version of this would be 3 a plus 1 absolute value cubed. Okay, so you can see how you got to be kind of strategic on how you're using these properties to make it into an easier form than it's presented. And that brings us to C. Where we were given C is the square root of 63 y cubed. Okay, and now since I'm using a square root, I want to be able to break this 63 up into where I'm going to be able to have a perfect square. So I'm going to think of the factors of 63. 1 and 63. The next one that jumps to my mind is 9 and 7. Okay, 9's a perfect square, and I'm trying to find the square root. So that makes it a very easy problem. Using the power property of radicals, I can rewrite this as 9y squared times 7y. Okay, I guess I can split it. Okay, and they're all combined. I can split it to make it easier for myself. Or if you wish, you could rewrite it as the square root of 9y squared times the square root of 7y. Okay, regardless, you're going to get the same answer because they're the same thing. So, can I take the square root of 7? It's not really a perfect square, so I'm going to leave that in the exact number as the square root of 7y. But this one here has two perfect squares, where 9 and y squared. The square root of 9 is 3, and the square root of y squared is just y. So my answer, the simplest version and the most exact version, is 3y times the square root of 7y. Okay? Any questions on those first couple problems or those first examples? Okay. Feel free to use the chat. Remember, I'm going to export them and then address your questions as I can if I don't get to them during the lecture session. So now I'm going to go to page P16. And we're going to talk about the key concept. Okay, key concept of rational exponents. Says if b is a real number, variable, or algebraic expression, and m and n are positive integers greater than 1, then b to the 1 over n is equivalent to the nth root of b if the principal nth root of b exists. Okay, so what this allows you to do, I know I'm pretty good when it comes to cube roots. I'm pretty good when it comes to fourth roots. Once I get to fifth roots and sixth roots, it's very hard to come up with them off the top of your head. This is a key because it allows me to use my calculator without having to just run multiplication back and forth. You can actually do this on your iPhone as well. I told you guys at the beginning that you wanted to get a TI-83. If you didn't get a TI-83, you can search in your app store and look for an app called Calculator X. Okay, I found it by just typing TI-83 into my Apple. I have an Apple phone, so my iPhone, where I buy all my apps and get all my fun games. If I can have a graphing calculator on my phone, which is very nice because it's one of the most useful tools you ever get. But the app that I found, it's free. It works great. It allows you to graph. And once again, it is called Calculator X. And it's going to make your life a whole lot easier when you're dealing with these type of equations, especially when you're getting to fifth roots and sixth roots and 16th roots. Anything higher than a square root or a cube root is a little rough. Okay, so we might as well use the technology and use the resources that are available to us to make our lives very easy. Because even though I know that 81 that the fourth root of 81 is 3, I could plug in 81 to the 1/4 power on my calculator, and then I would be given 3. Okay, all it does is make you more efficient. Technology is designed to make you more efficient. Okay, so that states once again that b to the 1/n is equivalent to the nth root of b. Okay, so it allows you to do square roots, cube roots, quartic roots, quintic roots very quickly. Okay, so now let's look at the second part of that. It says that b to the m/n is equivalent to the nth root of b to the m. Okay? So b to the m/n is equivalent to the nth root of b to the m. Okay, once again, it's very handy because you could come across a situation where you have to take the 16th root of b to the 4th. Well, that's quite a bit, you know. B to the 4th, that would actually simplify down to b to the 4th. All right? So using technology, once again, the name of that app was Calculator X. Okay, and we're looking at example 3. On P16, we have 2 more, and then I'm turning you loose. Okay, so it asks us, we want to simplify the 10th root of 32 divided by the 6th root of 2. Okay. Whew. All right. So the first thing that I would do in this situation, like I said, I'm pretty good when it comes to square roots. I'm pretty good when it comes to cube roots. But the 10th root of something, that's very hard to find without a calculator. I have to multiply a number against itself 10 times to get that answer. Okay, it's very difficult. A lot of arithmetic goes into that. So the first thing that I want to do is I want to use rational exponents. Okay, and notice I can't just divide those because we have different indexes. One is 10 and one is 6. So this can be rewritten as 32 to the 1/10th power, and this can be rewritten as 2 to the 1/6th power. Still an equivalent statement. Okay, so now I want to think to myself, I want to be able to get to the same base being 2. That way I can use my quotient power or my quotient property of just dividing exponents. If they have the same base, then I can just subtract exponents and it makes my life very easy. So I'm going to think of myself, 32 is 2 to the 5th power, or 32 to the 1/5 is equal to 2. So I'm able to substitute in 2 to the 5th or 32 and leave it raised to the 10th power or the 1/10th power. So now I'm making it simpler for myself to do all the work. Okay, once I've done this, now my power property of exponents is going to kick in. 5 times 1/10 is equivalent to 5/10 or 1/2. So this is 2 to the 1/2 over 2 to the 1/6. Okay. Now at this point, I have the same base. The key is I have the same base and I'm dividing them. They both have exponents. From the properties that we discussed at the beginning of class, this tells me I can subtract these. I can subtract these exponents. Or my answer is 2 to the 1/2 minus 1/6 as an exponent. So in order to subtract them, I need to have the same base. So I'm going to raise this to get to the 6th. Okay, so that's 2 to the 3/6 minus 1/6, which is equal to 2 to the 2/6 power or 1/3. Okay, 2 to the 2/6 or 2 to the 1/3. Once again, they're equivalent statements. And then, once I have it there at 2 to the 1/3, I reverse my rational exponents to find that the simplest form I can get this into is the cube root of 2. Okay, like any other properties, rational exponents, they work both ways. It can be given to us in a radical form. We can change it into an exponent. It can be given to us in an exponent form, and we can change it to a radical. Okay, but this chapter is all about using these inner working properties together to put them into their simplest form. Trying to make your life easy. Okay, then the last one that we have is example B. It says the fourth root of x to the 21st, y to the 15th. Okay, so the first property I want to use is the product of roots to expand those and get them to where they're separate radicals. That way I can use my rational exponents separately. Okay, so the first thing we're going to do, we're going to rewrite this as the fourth root. I'm going to make it bigger so that you guys can see it. Of x to the 21st times y to the 15th. Okay, so now that I have them separate, I can use my rational exponents to get rid of the radical and just be dealing with exponents and then be able to simplify them. So the fourth root of x to the 21st can be rewritten as x to the 21 over 4 power. Fourth root of y to the 15th can be rewritten as y to the 15 over 4. Okay, once again, I can't do product of powers because they have separate bases, x and y. So I still have to work them individually. But what I can do is I can separate this into two different forms and be able to get a whole number as an exponent. Okay? What I would do is break this into x to the 20 over 4 times x to the 1/4, because those two are equivalent statements. If I were to multiply these two together, I would end up with x to the 21/4. Okay, I'm going to do the same thing with my y's. Y to the 12 over 4 times y to the 3/4. Okay, and the reason I'm doing that is because I want to try to get whole number exponents. Okay, so I'm expanding that exponent to make it my life easier. 20 over 4 is going to simplify down to 5. So here's x to the 5th times x to the 1/4. Okay, and then this side would be y to the 3rd times y to the 3/4. And if you look, I've been able to isolate through rational exponents. I've been able to isolate x to the 5th and y to the 3rd. So those are going to be outside. And then I'm going to reverse my rational exponents. And my product of radicals and put them back together to get my answer. Okay, so it's using the properties to expand them, using the properties to condense them. And since I was able to isolate whole number exponents, I can move those to the outside of my radical. Okay, that makes sense. So my final answer, simplified version, is x to the 5th y to the third times the quantity of the fourth root of x y to the third. Any questions on that one?